Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is Accelerate your IoT development project with our MEMS 3-axis acceleration sensor. Our speaker today is Vinod Kumar Ramu, who is working as product manager in the field of sensor components at Würth Elektronik eiSos. He will hold today's webinar and also answer your questions. As we also take all possible steps against the coronavirus, we are unfortunately not sitting in the same rooms today, but are holding the webinar out of the home office. In case of technical issues or some delay, please take this into account. We will do our best to make a smooth process possible. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. Today's webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will also receive the link to the presentation as well as to the recording of the webinar only in the next few weeks. And now I will hand over to our speaker, Vinod, and I wish you an exciting webinar.
Thank you for the introduction, Marcus, and I thank all the participants who registered for today's webinar on acceleration sensors and how it could accelerate your IoT projects. I hope you're all staying safe from the current situation, so let's get started. So with today's webinar, I would like to start by talking about the basics of acceleration sensors and the capacitive sensing circuit, which could realize acceleration, and also the MEMS capacitive-based acceleration sensor packages and key parameters of the acceleration sensors, followed by operating modes. And also, I would like to show what is FIFO Buffer, why it has been incorporated into the acceleration sensors, how one could get used of FIFO Buffer for different IoT applications, and also few embedded features which are inbuilt in this acceleration sensors. And I'd like to show a couple of IoT use cases with a conclusion. Let's understand acceleration with a basic Hooke's law principle. Here, a spring of one end is attached to a fixed surface and another end is attached to an object of mass m. When a force is applied on an object of mass m, there will be extension of the spring. The force due to the spring tension is directly proportional to the spring constant and the extension of the spring. Similarly, on the other side, if you want to know how much force is exerted on an object of mass m, which we could realize from simple Newton's second law, where the force is directly proportional to the mass of an object and the acceleration. Here, the displacement of an object from the initial position before the force applied and after the force applied is referred as x in the previous case in Hooke's law, where x referred to an extension of a spring. Let's put these two principles together to find a relation for acceleration, which is directly proportional to the displacement of an object. So if we want to find the acceleration of an object, so displacement of an object is easily found with different techniques. Let's see what are the techniques involved to measure the displacement electronically. There are different techniques involved to find the displacement. There are three predominantly used techniques in the field: are resistive-based technique, inductive-based technique, and capacitive-based technique. As the name implies, with the resistive-based techniques, there will be a change in the resistance when there is a change in the distance, which is displacement. Similarly, for the inductive-based technique. For today's webinar, I would like to explain more about capacitive-based technique, because the sensor what we offer for IoT application is a capacitive-based technique. So the sensing element in our MEMS-based sensor is a capacitive-based sensing element. Okay, how it works. Let's take the previous example of a spring of mass M attached at one end and another end is fixed to a fixed surface. When we put a capacitor of parallel plate of one end on an object of mass M, which is flexible or movable, and another end of the parallel plate is mounted to a fixed surface. Let's assume the distance between these two parallel plates is x. So when there is a force applied on an object, there will be a change in the displacement, which displacement is equal to the distance between these two parallel plate capacitors. As we saw before, if we want to know the acceleration of an object, we need to know the displacement of an object from the initial position to the final position. With the capacitive technique, we can see here the capacitance value changes, which is indirectly proportional to the distance between two parallel plates. What we can realize from this, the displacement to find an acceleration and the distance between these two parallel plate capacitors is similar. So if we want to know the acceleration, we have to simply find the capacitance. That's how it is, quite simple. So change in the displacement gives a change in the capacitance, which indeed gives the acceleration of an object. In this slide, I would like to show how the concept what we discussed previously is incorporated on a MEMS wafer level. Here, the MEMS refers to micro electromechanical systems. I don't want to talk deeply about the production process or the processes involved to etch the surface to realize a capacitive sensing circuit. I would like to show more on the functionality side, how the structures are developed to realize a capacitive sensing element. As you could see, the one end of the capacitor is fixed to anchors, which is referred as black surface here, and another end is fixed to a movable plate, which is mounted to a fixed substrate using a spring on the top side and the bottom side. You could see here, similarly, when there is a change in the acceleration, there will be a movement of a parallel plates between the fixed plates of an anchor plate, which indeed changes the capacitance value. You could see one interesting thing here. There are several capacitors are connected or developed in the structural form to realize a capacitive sensing circuit. The reason for this is, as I mentioned before, we are talking about the micrometer range, which is a MEMS element. So the change in the capacitance of a single capacitor is in the range of picofarad. In order to have a useful or more capacitance, we need to connect many capacitors in parallel to have a change in the capacitance with a small change in an acceleration. So the final output of the change in the capacitance is converted into voltage, which is further used for digital signal processing. Let's see how the change of capacitance to voltage happens. As you could see, the anchor plates are drives through an oscillator, which drives the capacitance with phase shift of 180 degrees. So when there is no movement or when there is no motion, which indeed refers to no acceleration, that means there won't be any change in the output values at Vs. So there is no acceleration, then there is no change in the output. Similarly, when there is a movement on either on the positive side or negative side, here I refer positive, negative means the upper direction or lower direction, right direction or left direction. It depends upon how we interpret it. So when there is a change in the acceleration of any of the direction, the respective voltage changes, either on the positive side or the negative side. That's how the change in the capacitance takes place. Okay, let's understand how the block diagram of the typical MEMS acceleration sensor looks like. In the previous example, we saw a one-dimensional MEMS structure, which refers to single-axis acceleration sensor. In order to have three different acceleration sensor values, we have to put three different sensing elements for three different axes. Here, the x-axis refers to the x-axis sensing direction, y, and similarly for z. The three output from three different axes is multiplexed through a multiplexer and amplified to a variable gain amplifier, because the output from the three axes are variable, which refers to change in the capacitance depending on the acceleration it's applied on the surface. So why we have actually a multiplexer and only one set of digital signal processing blocks? The reason for that is in order to implement an analog to digital converter, which converts the analog signal to digital signal, we have to use analog to digital converter on the silicon level. So which should be implemented in ASIC, which is quite space constrained, and also the cost. So in order to have a less space, one ADC is selected with the help of a multiplexer. So this multiplexer multiplexes all three different axis values and then gives the output to the amplifier, where it amplifies the voltage what we needed, and then it's converted the analog signal to digital using analog to digital converter. And then comes to a filtering block. Then interesting thing about the acceleration sensor is the user or the application engineer who uses the sensor has access to the filtering block of acceleration sensor. What does it mean? Based on the application, a person could select the sensor to put into low frequency output values or high frequency output value. He could either select a signal such a way he wants to use only for low frequency vibrations or low frequency movements or low frequency motions. In that case, a customer or a person could select low frequency LPF filter. If he wants to use a high frequency signal, then he can use high frequency filter with the respective settings. And then comes an embedded function block where many features are added to the output values with the different digital signal processing blocks, which we will see later how it works and why it has been implemented, followed by a control logic and interrupt for the calibration and temperature compensation also takes place before this. Finally, the output values are available on the output interface pins, where a typical microcontroller could be used to read the output values from the sensor through I2C communication with a clock speed of 100 kilohertz or 400 kilohertz. Based on the application, this could be selectable. As you could see, the sensing element takes place at the front end, which is on the MEMS. All digital signal processing takes place on the ASIC level to realize the acceleration sensor. Let's understand how exactly the acceleration sensor package looks like physically. As you could see, the sensors are quite small. It has a very small footprint. The length is 2 mm and the width is 2 mm, height of 0.7 mm. It's pretty small, and that is also one of the advantages that one could use it in many IoT applications where there are many space constraints in the PCB board. So the MEMS die is placed on a PCB substrate, followed by a MEMS cap. Here you can see the MEMS cap acts like a bridge between the ASIC and the MEMS die. So the signal from the MEMS die, from the sensing element from different axes X, Y, and Z, is fed through ASIC through MEMS cap. So the change in the capacitance takes place on the MEMS element, which goes the signal from MEMS die to ASIC through a MEMS cap, and then all the digital signal processing takes place on the ASIC. Finally, the output values from the acceleration sensor can be read through the output registers through MEMS die package, which is mounted on the PCB substrate with physical pins, which are 12 pins. You could simply connect your microcontroller to these pins and then read the values. Let's see the technical parameters, how or what are the parameters are involved with the acceleration sensors. I don't want to go so deep into the specification because we already mentioned everything in our datasheet, and I don't want to just read the values of the sensor. So one could easily find it in our website, where you could download the user manuals or datasheet. All the informations are available there. I'd like to talk only one important parameters here, which is the operating temperature range. So the sensor could work from -40 degrees to +85 degrees, so which is quite good for industrial IoT applications. And there are special features about the sensors, which is also mentioned in our user manuals. And we will also see few special features on following slides. So the sensors, what we offer for IoT applications, could be typically used for the industrial IoT applications and vibration monitoring. We would see briefly for how much vibration or how much vibration one could measure with the acceleration sensor, what we offer. And one could also use this acceleration sensor to find the motion or tools or equipment monitoring in a production plant. So one more thing I would like to highlight here is the long life availability. What does it mean for the IoT? Most of the IoT projects or products are in a initial prototype phase. So with a long life availability of our acceleration sensor, you don't need to worry about whether the product going to be available after a few years when you are already in a production phase. So we certify that the product is a long life availability product. In this slide, I would like to talk important parameter of acceleration sensor, and mostly it gets misinterpreted or misunderstood. So what is that parameter? So there are two important parameters of the acceleration sensor, which is output data rate. What does it mean? As you could see with the name, so the sensor output values are updated with a specific rate. In our case, with our acceleration sensor, the upgrade rate could go up to 1 kilohertz. What does it mean? In a single second, in a 1 second, the output values are updated 1,600 times. It's quite fast for many IoT-based applications to monitor vibration or continuous motion in a production plant. Another important parameter is bandwidth. So output data rate, bandwidth is not the same. These are two different parameters. So the bandwidth is limited for the acceleration sensor, which is 400 Hz, which could be used for low vibration monitoring applications. So the bandwidth of the sensor is limited through a cutoff frequency of 400 Hz. What does it mean? So the sensor could work of a bandwidth up to 400 Hz. For more than 400 Hz of vibration monitoring anything, the sensor is not recommended. Why? We have chosen the bandwidth to be 400 Hz when the update rate is 1,600 Hz. We want to avoid the aliasing effect in the output signal. So as per the Nyquist theorem, it should be minimal twice the bandwidth the update rate should be. So we even did more than twice, it's 4 times. So in this case, till up to 400 Hz, our sensors are good to go to monitor the vibration. Okay, let's see what are the examples for the low vibration monitoring applications. So as I mentioned, the sensor could work up to 400 Hz. There are few applications one could use to find the vibration monitoring in for the IoT application. One of the predominantly used application for this product is unbalanced equipment, loosening of the equipment in a production factory, or misalignment of the motors, or low frequency vibrations. So with a bandwidth of 400 Hz, the sensor could measure these 4 parameters. More than 400 Hz, the sensor is not recommended to use. Yeah, and the topic is to see where exactly the acceleration sensor is useful in IoT application and why it has been useful. Let's understand it step by step. As I mentioned before, the acceleration sensor has a very small footprint. So the length of the acceleration sensor is 2 mm and the width is 2 mm, height is 0.7. It's quite small, which won't take a lot of space in a PCB, and it's very easy to integrate as the sensor size is quite small. The sensor offers 3 different operating modes. What does it mean? Based on the application, you could put the sensor into different operations. What are the different operations we will see shortly? What it gives is that the flexibility in the IoT application. So if you want to have a high performance output values, you could put the sensor into high performance mode. If you want to have a very low current consumption from the sensor side, you could put the sensor into low power mode so that the sensor consumes low current, which indeed reduces the current consumption of your whole product. And the third point is the FIFO buffer. We will see shortly why the FIFO buffer has been inbuilt. What it offers is one of the advantage of FIFO buffer is low current. In the sense, when you enable the FIFO buffer, when you want to make use of the FIFO buffer, the microcontroller should not, or you don't have to communicate with the sensor to read the values continuously. All the work is being taken care by FIFO buffer. So the FIFO buffer saves a lot of microcontroller communication time. I would even say that by enabling the FIFO buffer, the sensor would not depend on microcontroller. It just takes all the responsibility of microcontroller and does everything what it needs. And the fourth, the sensor offers I2C digital interface. So it gives a flexibility, or it gives an easy access of the acceleration sensor could be incorporated into RF modules. So it gives one more level of easy integration on a communication level with the RF module for IoT application. Last but not the least, the sensor has many embedded functions. These embedded functions stops or completely saves the time of a software engineer who needs to develop a lot of algorithm to set a threshold or duration to detect some movement or some state of a sensor. Example, sleep, wake up, tap functions, and so on. We will see how it works later. So what it does, as I told, the sensor does everything. It also does one more thing, which is notification and trigger through interrupt pin. So the microcontroller don't have to understand the output values and trigger the alarm or notification. The sensor does everything by itself. So let's understand the operating mode of sensor. So the sensor has 3 different operating modes. The first one is high performance mode, second one is normal mode, and third one is low power mode. Let's understand how the operating modes differ for different parameters. For example, in terms of resolution, how the operating modes differ. So if you want to have output values with high resolution, you could either select high performance mode or normal mode. Or if you have a constraint of a current, so where you have to put the sensor into operation with a low current consumption, then you could put the sensor into low power mode, but in that case, the resolution is limited to 12-bit. And one more important parameter is current consumption, which is also dependent upon the output data rate and also the selected operating modes. As you could see, the current consumption is quite different from 3 different modes. So if you want to have a very good data, that means very low noise, very high update rate of the values. So the current consumption here could be 150 microamps. But if you want to have a sensor to consume very low current, like even less than 5 microamps, it's even possible, but you have to select the output data rate accordingly by enabling the low power mode. So in that case, the sensor could go work in a current consumption of less than 1.2 microamps. So if you don't want to know or do any of these things, I would recommend to use the sensor into normal mode, where the current consumption is quite fair and also the low noise values from the output data. As I said, the noise also differs for 3 different operating modes. So the noise also has an influence from the selected full scale. So if your full scale is low G, then the noise is quite good. If you're selecting the high G, which means you're increasing the MEMS sensitivity on a higher range, then the noise could be more than the less full scale range. So based on your requirement, you could select what type of operating modes you want. In this example, for the noise, I took a reference of ODR of 200 Hertz. Again, noise is different from different operating modes, different full scale range, and different output data rate. Let's see what is FIFO buffer. As the name implies, FIFO buffer is a first in, first out buffer, which stores the values. As I said, buffer is one of the important key feature of the sensor where it completely reduces the communication of microcontroller to the sensor. So why it is useful? For example, if you are developing a product where it needs to be powered by battery, then we could make use of the FIFO buffer where the communication between the sensor and microcontroller could be reduced. How it works? The sensor has a FIFO buffer of level 32. So the output values could be stored in levels of 32 times. What does it mean? The first value which enters the buffer on the lower side is shifted up to 32 levels. So that means 32 levels are stored in the buffer. So how fast the data is filling in the buffer is directly proportional to the selected output data rate of the sensor. So if you are enable the sensor to work in 200 Hertz of output data rate, the buffer will also update the levels with the selected output data rate of 200 Hertz. That is one of the important points here. You could read the values similarly how you read the values from the output register. So there is no separate settings needed. And one of the important point for the FIFO buffer is it has interrupt functionalities. You could put many interrupts, how many levels are filled, how fast it filled, and how many data you want to ignore before you read. That could be handled using the interrupt functionalities. And obviously by selecting different operations for the FIFO buffer, which is explained very detailed in user manual. If you have any doubts, please refer to the user manual of acceleration sensor. A complete explanation for the FIFO buffer is already explained. Let's see what are the embedded functions of an acceleration sensor. So the acceleration sensor, what we offer, has 5 different features. The first one is sleep and wake up. Second is stationary or active, tap functionality, free fall, and orientation. All these embedded functions are already inbuilt. So the main idea of this embedded function is to take the less time and the energy from the microcontroller side. So the sensor does all the job of the microcontroller. So how each and every feature works, I already explained in an application note and also in a user manual. Please refer to our user manual and application note, how exactly it works. I don't want to talk about the settings involved and also the different parameters to enable or disable these features. Let's understand how our sensor, by enabling few embedded functions, could be useful for different IoT applications. I have considered for today's webinar only 2 IoT applications by enabling 2 features, which is stationary or active, sleep and wake up. In the first example, in order to monitor a burglar of a home, like somebody is entering your home when you're not at the home, and by mounting the sensor on a window, the sensor will detect all the motions before you leave the house till somebody is entering the home. So this sensor monitors all the acceleration values. When there is a opening of the door in an unusual way, the acceleration increases, and which indeed raises an alarm through an interrupt signal. In the second use case, which is goods tracking, in the goods tracking, it's similar use case like before, but in this case, it won't trigger any alarm. it will just log the data after a certain event. Here, the event is damaging of goods through a shock detection. If something happens to a good, so the sensor will start reading the data only after the high G value and then log the position of the damaged place through a GPS or GNSS module to claim for insurance. How exactly the sensor works in terms of current consumption, as you could see, the sensor is smart enough to handle the operating modes by itself without any communication from the microcontroller. After we enable these two sensor features, the sensor already puts the sensor into different operating modes in order to save the power for a better automatic power management. As soon as an event is detected, the sensor wakes up and it just changes the operating mode in order to give a high performance mode value data, which could be useful for many applications. In example here is the damage through shock detection, where you have to know whether damage is like happened at the 1G or 2G, 3G. In that case, the noise should be quite low to realize the damage through shock. And I implemented a special use case for an IoT application with 4 different sensor features. By putting all these sensor features together to realize or to detect if a human is falling or not, and if he fell, whether he's moving or not, and how long he's been stationary without moving. So in that case, the sensor could trigger an alarm with different interrupts, which you could see here, the sleep state, sleep change, and free fall detection. A detailed explanation, also different settings, has been explained in the application note of the acceleration sensor, which could be downloaded from the internet. Please check if you're interested in this application or IoT use case, where these settings don't need any communication between microcontroller and the sensor, where the sensor does everything and it just sends only the interrupt, which could be used as a trigger alarm. Okay, we are at the final conclusion part. So what are the takeaways from this today's webinar? So I'd like to give you 4 points that you could take from this webinar. The first point is the sensor what we offer is a MEMS-based acceleration sensor, where the sensing element takes place on the MEMS die level, and all the digital signal processing takes place on the ASIC. Put it together and the MEMS package could be realized as an acceleration sensor. And why our sensor is best suitable for IoT applications. There are 4 important points, obviously from many. So I like to only highlight 4. The sensor could put it into operation where it could consume less than 5 microamps, even less than 5 microamps in the sense like 2 amps, 1 amps, and 3 amps. It depends upon how the ODR is, as we discussed before. And the second point is it has a FIFO buffer where it stops the communication between microcontroller and sensor, where all the handling of the storing of the data takes place in the buffer. And third point is the embedded features. By combining many features, one could realize many use cases, which we saw before. So we have to be creative to put many use cases to understand the features better so that we could realize many applications without a lot of software development effort. And the last point is the IoT interface, which is easily connected to any RF modules for IoT application. And the third point is the parameters. So there are 3 important parameters I like to highlight for the sensor, which is the bandwidth, which I already explained, a motion or vibration, anything up to 400 Hertz is easily measurable and easily useful from the sensor. More than 400 Hertz, it could not be useful. So the sensor has an update rate of 1600 Hertz, which is quite fast compared to other competitors. And the third point is the low acceleration. So the maximum acceleration with this low G sensor is up to 16 G. Last but not the least, how you could accelerate your projects with this acceleration sensor. So we're offering 2 different things for your projects. On a hardware level, we have evaluation board, where you could test our parameters or functionalities of the sensor or your ideas by easily mounting the sensors on a breadboard or connecting through a SMD connector. with the help of sensor drivers. So in the sensor drivers, we have two different packages. We have a header files and then C file where all the functionalities are written. And we also have a main file where is an example to read value from the sensor with three different axes, X, Y, and Z with different operating mode settings. That's all from my side for today's webinar. I thank you all for your attention, and I am waiting for your questions to answer. Thank you.
Yeah, thank you also, Vinod, for this interesting presentation. And as you have mentioned it, we would like to turn our attention now to your questions, and we wait a little until some questions come in. If we can't answer your question yet, we will answer them via email after the webinar. So we have a look at the first questions. Vinod, first question. Is there an embedded feature for orientation detection? And if yes, is it 4D or 6D?
So there are two different options, like how we explained, 4D or 6-dimensional detection. Both can be detected using orientation detection feature. So the answer is yes, we can detect the orientation, and the orientation could be either 4D or 6D.
Okay, so thank you. Then we have a look at the next questions. You have now the opportunity to ask us. Yeah, then Vinod, I see the next question. What is the update rate of the FIFO buffer?
The update rate of the FIFO buffer is same as the selected output data rate. So what does it mean? Like how fast the output registers are updated is same as how fast the FIFO buffers are filled. So what you select for the sensor to update the output values, it's same for the FIFO rate. So the minimum what the sensor could update is 12.5 Hertz. The maximum it could go up to 1.6 kilohertz. So it's user selectable.
Okay, thank you for the explanation. So as we have a look at the next questions, just a hint from me, you will receive the link to the presentation as well as to the recording of the webinar in the next few weeks. Okay, Vinod, then let's come to the next question. What is the maximum acceleration that the sensor can withstand?
So here, the maximum acceleration that the sensor could withstand, we have to go one step behind and see how the MEMS structures are manufactured. So the resonance frequency of the sensor is 3.4 kilohertz. So the maximum acceleration, each direction the sensor could take is 3000 G. So the maximum I would say is 3000 G.
Okay, so that's a lot.
Yes, that's quite a lot for a small sensor, right?
Okay, so if we can't answer your question yet, then we will answer them via email afterwards. And we have a look at the next questions. Yeah, Vinod, what is the resolution or the noise and stability of each axis?
So I have mentioned in the slide the resolution. For the maximum, it could go up to 14-bit, and the minimum is 12-bit. So the resolution to the noise has no direct connection, but the resolution is directly depend on the selected operating modes. So there are only 3 operating modes, and you have only 2 options. So either it could be 14-bit or 12-bit. With the noise, on an average, with a moderate output data rate, which we saw as an example of 200 Hertz. It could be 90 micro-G, I would say that is the moderate, but it could go even up to more, to 200 micro-G or 700 micro-G, which we saw in the low power mode. But in the high performance mode, the less noise from the output data is around 900 micro-G. And the stability of the each axis, I would say, I would answer this question by giving some parameter values. So the stability of in each axis is 20 milli-G. So the offset, I'm talking of the whole 3 axis, is 20 milli-G for the whole temperature range.
Okay. So thank you for the explanation. So now we have a little bit time for the next questions. Yeah, then let's have a look at the next question. What is the resonant frequency of the sensor?
So the resonant frequency of the sensor is, as I mentioned, it is 3.4 kilohertz for X and Y axis. For Z axis, which is normally pointing when the sensor, if the sensor is placed horizontally, the active sensing element is the Z axis, but there the resonant frequency is less than other 2 axes. So the value for the Z axis is 2 kilohertz. For X and Y axis is 3.2 kilohertz.
Okay. So then we will have a look at the next questions. Okay, so as I can see, we have some open questions already, but we will answer them after the webinar via email. And if there are some more questions, we will now have the time. We wait a little until maybe a question come in. You also have the opportunity, if you have open question after the webinar, just email us with the email eisos-webinar@we-online.com. Okay, so then I think we got no more questions. So now we are finished with our webinar, and if there are any questions left now, we will answer them by email afterwards. So thank you very much for your attention, and I hope you enjoyed our webinar. Also, big thanks to you, Vinod, for this great webinar.
You're welcome.
I hope you will hear us at our next webinar, and I wish you all a good day. Goodbye.